So let's talk about waste. In biopharmaceutical processes, there are many sequential activities which require control and coordination in order to deliver the desired high-quality product. The goal is to establish practices which will produce opportunities to reduce TIMWOD. And this presentation will review the 7 forms of waste, aka MUDA, and this can be extended further to cover MURA, aka workload unevenness through supply volatility, and MURI, aka peak period overburdensome workloads caused by unevenness, and we'll review opportunities for how we can reduce all these forms to produce a more efficient biopharmaceutical process. So thinking about waste reduction, there are 7 general forms of waste that have been identified, and these are often characterized using the acronym TIMWOD. Using this acronym, T stands for transport and can refer to both data and the transport of things, where things can be raw materials, product, in-process materials, or components. Inventory stands for I, and this usually refers to poorly managed stock. M means motion, and this usually refers to the motion surrounding people and people movement around a facility and a process. W stands for waiting, and this includes delays and backlogs, both for data and in the process and for people. O stands for overproduction, which means making too much. O also stands for overprocessing, which can involve unnecessary handling of materials, data, and the like. D stands for defects, where things are not made right first time. So let's look at each one of these individually, starting with transport. If we use a modular platform, then the potential for damage resulting in loss can be reduced. If we look at inventory, a modular-based single-use filtration system can reduce the number of parts needed, which can prevent mix-ups, together with resulting in a reduction in storage space required for key components. In terms of motion, non-configured or badly configured single-use assemblies can result in wasted material associated with pre-assembly. If these are arranged into modular units, this can save time and reduce motion MUDA. Waiting. Since setup is a big piece of an operational run, using a modular filtration system and assemblies can reduce up to 50% of this wasted waiting time by providing greater flexibility. In terms of overproduction, the correct sizing of modular components prevents the overproduction of material and controls the processing time much more tightly. Looking at defects, using a poke yoke application of parts to assure correct assembly prevents the occurrence of errors and encourages a standardized workflow in relation to the process practices. So looking at our biopharmaceutical process, there are some areas to focus on in order to reduce the waste. Some key areas include the efficient control of raw materials and the efficient control of processing time, better control of equipment use and processing setup times, a reduction and a higher level of control of equipment during changeover, more efficient utilization of the available space through implementation of good flow patterns, simply put, the correct equipment for each task required, better use of equipment for the process task, tight coordination of sequential activities in order to generate smooth flow and prevent bottlenecks, a good understanding of what the appropriate level of staffing is for a required process, poke yoke mistake proofing of the equipment and the processes, and a continuous tight attention to equipment maintenance, especially preventive maintenance. So looking at a few of these areas, we can give some ideas and examples which will illustrate the opportunities open to the lean practitioner. Looking at a few examples, we can better illustrate what we're talking about here and quickly relate real situations to demonstrate where these principles have quantifiable applicability. Slide 4 here demonstrates the efficient control of raw materials. This is a complex process that involves upstream supply chain activities connected with vendor management, the supply of the materials, and the acceptance testing at the site by the facility quality control departments. If we consider the following points, on-time delivery and warehousing at the site can be regulated to reduce transport waste, overstock of inventory waste, unnecessary motion waste, waiting waste associated with testing, over-processing waste associated with unnecessary testing of components, and all materials that are delivered in split lots, as well as defects waste due to materials and components that do not meet agreed supplier specifications. Slide 5 illustrates the effective control of processing time. This can include reducing all waiting waste due to unnecessary hold periods or inefficient lead time coordination with production needs. This leads to a reduction in motion waste due to better coordination of serial unit operations and processing steps, a reduction of work in progress due to a tighter control of production, which reduces overproduction waste, production leveling, which reduces over-processing waste as product is made to a customer-mediated takt time, which frequently results in fewer defects due to in-process deviations. Slide 6 refers to the efficient utilization of the available space. Through the implementation of good flow patterns, material, people, product and data flow can play a huge role in waste reduction in a biopharmaceutical facility. Where possible, unidirectional flows are the preferred design for biopharmaceutical facilities, where the regulatory compliance needs for the separation of clean and what are called dirty process streams is required in order to maintain current good manufacturing practice operations. In modern facilities, modular approaches are being utilized to reduce excessive motion, assist with defect generation, reduce over-processing aspects, eliminate unnecessary holding steps, and reduce operating travel motion by the facility personnel. The use of spaghetti diagrams permits the derivation of the best designs and best practices for the operation of these facilities and will have a good and significant impact on the level of compliance and productivity attainable by these facilities as a result of their application. The laboratory end of the manufacturing operations can best be illustrated through a modular processing and analysis approach, where the analytical modules reduce processing time by as much as 60% over similar processing using a non-modular approach to sample analysis. Slide 7 takes into consideration mistake proofing, often called poka-yoke. In processing industries like biotechnology, where material flow requires input from both machines and human beings, there will always be mistakes, defects and errors introduced into the mix. To think otherwise is to be unrealistic, since both have their respective frailties. The important goal is to define and focus on is how to reduce errors and where possible to eliminate these completely. Aligned with this point is the goal of doing things correct or right first time. Poka-yoke is conjoined with this goal since it means to mistake-proof operations so that these things don't happen. Catching errors means that product defects will not occur, so the goal is to produce an error-free environment wherever possible. This technique is intended to increase quality through the capture of defect-causing problems and then performance of immediate remediation plans to remove the problem. Poka-yoke encourages the use of simple, low-cost solutions to bring about an improvement that reduces the occurrence of defects. Such systems can be mechanical devices such as a valve, which may direct the flow in only one direction, an electrical device that only operates according to a particular flow, or a physical measuring device that aids in the flow of a process. Alternatively, the Poka-yoke solution will be a procedural device which might prevent a task from occurring until a supervisor has reviewed the completion of the preceding task in the process sequence. All of these are good examples of poke-yoke mechanisms. So in summary, we can see that by the application of TIMWAD for the reduction of waste in biopharmaceutical processes, we can have a dramatic effect on the overall efficiency and compliance of these processes, which can only be good for the industry moving forward.